Hi class, welcome to week 6 module. We're looking at linear regression and correlation concepts this week. What we're looking at is when you have two sets of data that are paired, and we're going to typically call them the X the X data and the Y data, but they're gathered when you collect the data. You gather the X and the Y in pairs, and so we want to know whether a linear relationship exists between the sets of data. So that's what a correlation is talking about, a linear relationship. So if you were to plot the data, do you get a line or do you get some other kind of shape? So the correlation between the two sets of data can be quantified using a statistic, a descriptive statistic called the correlation coefficient. The calculation of a correlation coefficient can be a little tedious, so I'm going to show you some of the tools in StatCrunch that can help you calculate it. So we're looking now at problem number 3, and so it gives you a data set. Click on this to look at the data set. It's very relatively small data set, but remember, this icon always allows us to copy it into StatCrunch. So I'm going to show you how we can do all of the tasks here. We're going to first thing we're asked to do is to draw a scatter diagram of the data. So from here, under the graph menu, the scatter plot is what we want. So for scatter plot, for the x variable, select x. For y variable, select y. And everything else looks fine. There's no need to display any of this other stuff. We want to display points, but all of this is just optional. Leave it all blank. Point type, all of this stuff is fine, fine, fine. Let's just hit compute and take a look at the scatter plot. Oh, here's the thing though, that this thing is it's not going to look exactly like this, because this thing the axes cross. When I click down here, and I got some options for the x-axis and for the y-axis. So if I set the x-axis to go from 0 to 10, and if I set the y-axis, set that from 0 also to 10, what we're going to have in this picture is going to very much look like one of these plots. So just looking at it, you can see that it looks just like this plot here, right? This point, those two, and those two. Okay. So it asks you by hand. Well, I don't want you to do this by hand. I want you to calculate the correlation coefficient using StatCrunch. So again, under stat, we're going to go to the summary stats, the correlation summary stat. And again, we're going to hold down Control when you click the X and Y. They both have to be selected here. And what I want to also do is display a two-sided p-value. So what that's going to do is going to allow me to decide whether the correlation is strong enough for me to conclude that there is a linear relationship. So it's just going to give you this little bit of information. The correlation between x and y, it tells me, is this negative 0.2738. So that's the correlation coefficient. I'm going to copy that here, but I have to round this to 4. And what does this mean? So the correlation coefficient is negative, right? Clearly it's negative. The absolute value of the correlation coefficient is 0.274. So what's the critical value for this data set? If you look back at the data set, or let's just look at it here. So you can see we've got we've got 5 points of data. And then you actually just count the points on here. What this is asking you to do is to look at this critical values table. The table, when I click on this, it's going to pull it up. So this is saying if I have 5 points of data, I would only conclude a linear relationship if the absolute value of the correlation coefficient, which is absolute value is when you take away the negative sign, right? If the absolute value is bigger than 0.878, then that's strong enough for me to conclude there's a linear relationship. Now, 0.878 is the critical value. This is not greater than the 0.878 that the table gives me. And so therefore there is no linear relationship exists. That's the steps you do for concluding this. So we take the absolute value of this correlation coefficient, compare it to the table where we have n is 5 points of data, 0.878. That's the critical value. We need to exceed that critical value in order to conclude a linear relationship. Okay? Okay, so we're going to do a similar thing here. We've got another set of data, and we're going to let's read this. A pediatrician wants to determine the relationship that may exist between a child's height and head circumference. She randomly selects 8 children, measures their height and head circumference. Okay, so if the pediatrician wants to use height to predict head circumference, then height is known as a explanatory variable. Height is explanatory, and the response is the head. So the predictor, the thing you're trying to use to predict, that's called explanatory. Sometimes it's called predictor as well. And the other one that is what you're trying to predict, which is in this case, in this case we're predicting head circumference, so that is we call the response variable. Okay, draw a scatter diagram. Again, let's do this in StatCrunch. Open this data in StatCrunch. And we're going to graph a scatter plot. Where did it go? Scatter plot. X variable. We want head. Let's see. The explanatory variable should be x. So height is x. Y is going to be head circumference. Since we're using we're using height to predict head. That's where we want to assign them. Horizontal should be height. Vertical should be y. Should be head circumference. Okay. Everything else should be fine, and I'm not going to be concerned with the axes, so I'm going to just click compute and take a look at this. So I'm going to put this over to the side, make this a little smaller. Okay. So just looking at it, it looks like this one looks, see, these two both have the same shape as this, but the values might be a little off. Let's just check. Oh, look at these two graphs, they look right, but you can see that the axis, this one is height, whereas that's circumference. What I want is height to be down below and circumference up above. This is the only one that matches the shape and has the axes labeled correctly. Okay, now compute the correlation coefficient. Let's go back to here. We can do the summary stat correlation. Pick the two variables, and we'll again, I guess since we're using a critical table, we don't have to use the p-value. I didn't even talk about that p-value. This time I'm going to mention why I put the p-value in. So, okay, the correlation coefficient is 0.9537. So I'm going to round that up to to 0.9, what was it, 954. Let's see, just make sure, 0.954. I have to round that up. Okay, 3 decimal places, looks good. Does a linear relationship exist? So we can conclude this based on this p-value. The p-value is very, very, very small, right? The critical values that it's giving in the table correspond with what we would call a significance level of 0.05. So rejecting when the absolute value of the correlation coefficient exceeds this critical value is equivalent to concluding a linear relationship if this p-value is less than the significance level. So I know from this p-value it's less than 0.05. So I would conclude yes, 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 there is a linear relationship. From this table, I would say, okay, well there are, what is it? There is not eight points of data. So for n equals 8, 0.707. So I'd only need a correlation coefficient exceeding 0.707 to conclude a linear relationship. And yeah, this is above that. So there, yes, there appears to be a positive linear relationship because R is positive and not less than the critical value. R is positive and it's greater than the critical value. So that's called a positive linear relationship. Okay, cool. Okay, so here we're going to calculate the correlation coefficient for both this very tiny set of data for females and tiny set of data for males. Open this in StatCrunch, and this is where the choice of columns for correlation matters. I'm going to do it separately because I think if I selected all of them, I don't know. I think it's gonna calculate correlation for everything. So I'm just gonna do these two and hit compute. Okay, this is for females and 3 decimal places. That means I'm gonna take negative 0.008, and I'm gonna go back to options. I can just change it to males and compute. 0.158, groovy. Okay, so we got our correlation coefficients. Okay, so looking at this, the correlation coefficient for females is very close to 0. So I would say there's no linear relationship. And for males, that's also quite a low linear correlation, 0.158. I would say that's also close to 0. And so I would say there's no linear relationship. You can, in order for there to be a linear relationship, you'd really need to have much stronger, especially with 3 points of data. If I could go back and I could include the two-sided p-value. So the p-value of 0.8987, that, remember, a p-value in this case is measuring how likely it is that there's no linear relationship. This means there's really a strong, strictly speaking, this isn't totally correct, but I'll say there's a strong amount of evidence in favor of no linear relationship. Okay, so, but you can also say that. I mean, 0.15 is pretty low. Okay, great. Let's see. Now we're talking about linear regression. For number 6, we want to find the least squares regression line. To calculating a line, a regression line, is very, very easy to do in StatCrunch and very tedious to do by hand. So I'm opening up the data in StatCrunch. Under Stat, I want to go down to regression. and I do a simple linear regression. Simple linear regression means I have the y values, which are my response, and I have the x values, which are my explanatory variable. And a multiple linear would be you have multiple explanatory variables for a single response, but we're not doing that in here. A simple linear, we have x and y, that's it. For x, I select x. For y, I select y. Very simple. And you can leave the hypothesis test here. It's going to give you a lot of extra information, which you don't have to use all of. Really, all we're looking for here is, you can see this, it gives you the linear regression equation. That's what we're going to be putting into our answer. So now be careful, because it's giving you an intercept and it's giving you a slope, but the way this is giving it is the slope goes first and the intercept goes next. So the slope is the number that multiplies x, and the intercept is the number that just is added to it. Okay, so 4 decimal places. I'm going to just copy, well, I'm going to type it in because I can see it. It's 1.7568 is the slope, and the intercept is a negative number, negative 3.8919. Okay, 4 decimal places. I rounded that up. Great. Let's see. Okay, choose the correct graph. So let's take a look at what the graph would look like. Again, you go to graph. I'm going to go to the scatter plot, and I'm going to check off one additional option I didn't do before. Choose my x, choose my points, and what I want to overlay a function on it. I can overlay the function directly, or I can, if I overlay a polynomial order of order 1 and I choose the best fit, the polynomial order best fit, that's a linear model. Okay, so you can I can explicitly choose best fit, or I can put in the intercept and the slope here, but I'm going to do the best fit. The best fit line is exactly what we found, the least squares regression line. So it'll overlay the best fit line. Okay, this is great. So this compared to what we have. Now I'm gonna just so that we can see it better, I'm going to match up the axes, starting with looks like I want to have this going to my x-axis. I'm going to go from 0 to 10, and the y-axis I'm going to go from 0 to 13. This is the reason I'm doing this is I could see this data goes up as high as around, like 9 is this highest value, and so I want to go up to 10. That's like a little bit higher, and then for the y's, it's going up to 12. So I'm going one tick higher, up to 13. This matches the options here, and you can see the only one that really looks good is this one. In fact, it looks quite good, doesn't it? Yeah, I'd say that looks pretty great. Okay, so let's check it. You can, of course, also you can look at this and just check the points one by one and see if they match up with the points that are given in the data. That's also fine. You can do it that way. Okay, let's see. This looks like the exact the sum of the squared residuals. Oh, okay, this is a different one. So let's talk through this problem. Okay, so again, I'm going to open the data in StatCrunch. It just takes a few moments. I'm going to find the least squares regression line under, remember, it's stat regression, simple linear regression. I'm going to select my variables, x and y, and I don't have to pick anything else. It'll give me all the output that I need for to answer these questions. So, okay, there's a lot of stuff here. The least square regression line is given. I'm going to get for the slope, it's actually a negative number, negative 0.92, and the intercept is the 120.2. Okay, great. The sum of the squared residuals. So the sum of the square residuals is given, it's given here in the analysis of variance table. So I'm very briefly going to talk through it. The model, this SS stands for the sum of squares. Okay, residuals are how far off from the data your model is. So the residuals for each data point, you can calculate its residual by seeing what would this model predict for that x value. So for example, let's pull up. Okay, great. So let's calculate a residual. So take this first data point, 20. Okay, what would the model have predicted? Let's just punch in negative 0.92 times 20 plus 120.2. Okay, the model would have predicted 101.8. Now the actual value was 99. The residual is calculated by taking the actual value, 99, and we subtract what the model would have predicted, 101.8. This number I just have here is the first residual. Okay? So if you were to calculate a residual for each one of these, you would have 5 numbers. So the sum of the squared residuals means you square each of these numbers. So you take 2.8 squared and add that to the next residual squared plus the next residual squared, and so forth and so forth and so forth. Now, the output from linear regression actually gives you the sum of the squares of residuals right here. So the residuals can be considered errors. So the sum of the square of the errors is what we're looking for. Sum of the square. Now it's rounded up to 1 decimal place. I hope that that's not a problem. Yep. Okay. Let's see. Student at a junior college. A survey of 20 randomly selected full-time students. So this is the model that he gets. Okay. So he's saying for somebody who plays X hours of video games, he predicts a grade point average of Y. So in this case, we're going to do this directly in the calculator. I'm going to do just what I did before. I'm going to take X equal to 8 and I'm going to put it into this formula. So negative 0.0505 times 8 plus 2.9259. Check that, make sure it looks right. Okay. So this is what the expected grade point average would be to the nearest hundredth. That's 2.52. Okay. The slope for these problems can be interpreted that 1 unit increase on the x is going to result in that slope of a change for y. So in this case, an additional hour, 1 unit is an hour, is going to result in a decrease, right? Because the slope is negative, it'll be a decrease of 0.0505 on average. Okay, so what is the y-intercept interpreted as? So the y-intercept is interpreted is if the x value is 0, this would be our prediction. So what does it mean for the x value to be 0? X is how many hours a week somebody plays video games. So this is saying this is the average, this would be the average grade point average for a person who plays no video games, right? The average grade point average of a student who does not play video games, yeah, is going to be 2.9. All right. A student who plays video games 7 hours per week has a grade point average of 2.45. Is the student's grade point average above or below the average among all students? So let's just see, what would the model have predicted, right? That's what it's really asking. The model would predict negative 0.0505 times 7 for 7 hours plus 2.9259. Okay, the model would predict 2.5724. This guy has 2.45, which is less than what the model would predict. The student grade point average is below this. His GPA is below the average for those because it's less than what the model would predict. Excellent. Don't need that. Let's see. An author of a book discusses how statistics can be used to judge both a baseball player's potential and a team's ability to win games. On-base percentage is a predictor of winning. Okay. So it looks like this is similar to before. I'm going to let's go through it real quick. Okay, so for this model, X is the on-base average, on-base percentage, and Y is the winning percentage. Okay, so the slope is for each percentage point increase for the X, which is on-base percentage. For each percentage point increase on on-base percentage, the winning percentage will, this is a positive slope, so it would increase by 2.96. So D is the only one that says what we need. In a 1 percentage point increase for on-base, the winning percentage will increase by this 2.96. The lowest on-base percentage was 0.32 and the highest was 0.362. So, yeah, think about it like this. The y-intercept, it only has any real meaning if a value of 0 for x is realistic, right? It's saying that in the data set, the lowest on-base percentage was 0.32. So nobody had an on-base percentage of 0. So it wouldn't make any sense realistically to put 0 in here. So this negative 0.4877 for an intercept doesn't have any real interpretation. Whereas in the previous problem, it does make sense for a person to play 0 hours of video games. So it does not have a useful interpretation. So the other thing is interpolation and extrapolation. So extrapolating from a data set means we're trying to extend the linear model past what our data had as a sample data. So look at this, we are told that in the data set, the lowest value of x was 0.32 and the highest value was 0.362, which means this linear model is really only good for regression for inputs in that range. So if somebody has an on-base percentage of 0.24, that's really outside of the range for our x value, so it really doesn't, it would not be a good idea to use this model to try to predict their winning percentage, because that just wasn't that's extrapolating from our data set. Okay, it's not going to be a good idea. Okay, so now we're going to calculate a residual. So for an on-base percentage of 0.322 and a winning percentage of 0.544, what's the residual and how do we interpret it? So remember, residual, we put into the model 2.96 times this on-base percentage 0.322, that's the x value, and then we subtract minus 0.4877. Okay, cool. So this is the residual. I'm sorry, this is what the model would predict, and the actual was 0.544. So we always take the actual value, 0.544, minus the predicted value, 0.46542. So this is our residual. 4 decimal places, I could do that, 0.0786. The residual, what would we say? We would say this person had a higher winning percentage than the model would predict. So what are these options? The winning percentages of the team and the on-base percentage of the other team do not vary. What? The residual indicates that winning percentage of the team is above average for those. That's exactly what it indicates. It's above average because it's a positive residual. They did better than the model would have predicted. Yeah, and the other, yeah, that's the only one of these that makes any sense. Okay, so this homework set is taking a little longer, but hopefully this is helping you feel a little bit better about these problems. Let's see. So cola replaces healthier beverages, and cola contains caffeine and phosphoric acid. Researchers want to know whether consumption of cola is associated with lower bone mineral density in women. The data shown in the accompanying table represents a typical number of cans of soda consumed in a week and the bone mineral density of the femoral neck for a sample of 15 women. Okay, all this stuff. Okay, so we're going to be doing this again. Let's pull up our data set. Okay, and let's open it in StatCrunch because that's what we're doing here. All right, great. So under stat, we're going to do a regression, simple linear regression. We've done it a few times at this point. Okay, pick our x value, x variable, oops. So what are we trying to predict? We're trying to predict based on number of cans of cola. We're trying to predict bone mineral density. It doesn't make sense to do it the other way. The predictor should be something that we know, and the response should be something that we don't know. It's like in a study you could control for the cola, but you couldn't control for bone marrow density. Bone mineral density, not bone marrow density. Okay, so here's our regression output. This giving us the line. You can see the what is it? The intercept is 0.88, 0.885, and the slope is negative 0.28. So let's try to get these in the right places. The least square regression line is, so we want 0.88 positive to be the intercept and a negative 0.0029 to be the slope. That's the one that matches. Interpret the slope. For one additional can of soda, bone marrow density will decrease, because it's a negative slope, by this number, 0.0029 on average. Okie dokie. Let's see. The intercept. Does the intercept have meaning? Well, the meaning of the intercept would be for a person who consumes 0 cans of soda per week. Does that make any sense? Sure, why not? Some people don't drink any soda, so the intercept would be for a woman who does not drink cola, the bone marrow density, nope, that's not the intercept. The intercept is here. Yep. Okay. So let's see. 4 cans of cola. So, okay. I'm going to scroll up so I can see my regression line and go back to my calculator. I'm going to predict for somebody who drinks 4 cans of cola. So I'm going to put 4 in for x. It's negative 0.0029 times 4 plus 0.8858. Okay, so that's what we would predict for their bone marrow density, or bone mineral density, 0.8742. 4 decimal places, looks good. Okay. And if some woman who drinks 4 cans of cola has 0.873, that is a little bit less than what the model would predict. That's below average. Would you recommend using the model to predict the bone mineral density of a woman who consumes 2 cans of cola per day? Well, let's just take a look at our data set. In the data set, do you have any people who have 2 cans of cola? Sure, there's a couple. It goes from 0 to 8. So there's nothing, we're not extrapolating from our data set if we predict for 2 cans. That's totally safe. Oops. Okay. So that's clearly something is up with that. Why would you recommend using the model found in Part A to predict the bone mineral density for a woman who consumes 2 cans of cola per day? Oh, you can see the mistake I made. This could very well be the mistake you make too. I didn't read the problem very carefully. I was reading this predictor is the number of cans of cola in a week, not in a day. So 2 in a day means you'd have 14 in a week. Okay, 14 in a week is beyond what we have in our data. We only go from 0 to 8 in a week. So 14 in a week is beyond. So no, we wouldn't want to. I made that mistake. Don't make the same mistake I did. Okay. We don't want your hints. Okay. So it looks like this is more of the same. This looks like pretty short. Let's see. Given a data represent the total compensation for 10 randomly selected CEOs and their company's stock performance. Let's just pull up, since we have the data, let's just pull up the data in StatCrunch. I actually didn't even read the problem, but I'm assuming that this will be helpful, so let's see. Okay, so we have a correlation coefficient of that. What will be the predicted stock for a company CEO who makes 15 million? Okay, so this one here, number 11, is making us really think critically. The given data represents the total compensation for 10 randomly selected CEOs. So I pulled up the data in StatCrunch. Now, okay, so you can see what we got here. And it gives it to us that the R, the correlation coefficient, is negative 2.021. So we are asked to predict the stock return for a CEO that makes 15 million. Now, if a linear model was appropriate, we would do linear regression and create a linear model and use that, plug in 15 million for X and see what we get. But the fact that the correlation coefficient is rather small makes us want to check this critical value. So we're told we have 10 CEOs. So 10, a critical value is 0.632. so the absolute value of this, which is to say take away the negative sign, does not exceed 0.632. So bottom line is a linear model actually isn't appropriate. So there's no point in doing linear regression for this. The best prediction we can make for these CEOs is to just look at the average of our data. So all I'm going to do is calculate for the column data the stock return. So the mean stock return is 17.27. So 17.3 is the average. That's what we would predict. We don't have enough of a linear relationship for us to use a linear model, so we're just going to average those stock returns, and that'll be our prediction. Whether he makes 15 million or 17 million, we're not going to have any difference in our prediction. Okay, so we're going to look at a residual plot now. Residual plots. The residual plots, if for a good linear model, a residual plot should be pretty much should have pretty much no real pattern. You shouldn't be seeing a curve or what you want to see is just it should look like a random smattering of the dots all over the place. The only thing about this that is a little bit suspect, I would say, is these 2 points down here. So I wouldn't, it looks like there's, so what are these 3 things? Pattern residuals. Is there a pattern, like a curve or something like that? No, there's no pattern. It's pretty random. Is constant error variance. This is to say the spread, how far spread out it is, should be pretty much the same going across. I'd say, yeah, I mean, that looks fine. It's still pretty spread out, except, of course, for these 2. Those 2 I would call outliers. And so only for those 2 that might indicate that a linear model might not be appropriate. It could still be appropriate, but that's the one thing that's a little bit suspect, is those things. I would call them outliers. Okay. Let's see. So, following data table. So it's giving us a residual plot and a scatter plot. Now, I want to actually show you how we can create the scatter plot or the residual plot in StatCrunch, because it's useful to know that, to know how to do that. And since it's asking us to look at the residual plot, we could click there and look at the residual plot, but I want to, just for argument's sake, I want to create a regression. I'm going to graph the, let's see, the residual plot. Oh yeah. Okay. So we pull up the simple linear regression, select our x variable and our y variable. There's a lot of options down below. If you scroll down, you've got graphs, a residual index plot, residuals versus x values. That's what we want, residuals versus x values. So we're going to, in addition to getting our linear model, we're going to get residuals versus x values. You can also get the fitted line plot. That's kind of nice. But that's all I really want right here. Yeah, you know, might as well get the fitted line plot as well. I'm going to hold down Control. Compute both of these things. So we get our output from linear regression. If you click there, we have our fitted line plot. Click again. This is our residuals. So looking at these residuals, this looks like a very nice residual plot. Things are scattered around, spread. I would say this looks fine. So does it confirm the relationship is linear? I would say, yeah, the plot shows no discernible pattern, so a linear model looks fine. The coefficient of determination is 88.4. So let's go back to talk a little bit about the coefficient of determination. And you can see it right here. R squared, 0.8848. So 0.884, 88.4%. The correlation coefficient tells you whether it's a positive or a negative linear relationship. If you square that number, you get what's called R squared. R squared is always positive because you're taking a number and you're squaring it. Also, R squared is going to always be between 0 and 1 because your R is between -1 and 1. When you square it, it's going to be between 0 and 1 now. Okay, so R squared has a very clear interpretation, and it goes like this. It says what percentage of the variability in the X variable can be explained by our model, or can be explained by, what percentage of variability in the Y variable, the response, is explained by our X variable. Okay, so back here, it's saying the least square regression explains 88.4% in the variation of length. That's right. Length is the response variable, so we are able to explain 88.4% of the variation. And that is what R squared means. All right, great. So the time for a planet to complete its orbit around a particular star is called the planet's sidereal year. The sidereal year of a planet is related to the distance the planet is from the star. The accompanying data shows the distances. Okay, so let's open up the data set for 9 planets. A particular star. Okay, so draw a scatter plot of the data treating distance from the star as explanatory variable. Okay, let's do it. Let's graph the scatter plot. So you know how to do this at this point. X variable, distance from the star. The Y variable should be the sidereal year. Okay, compute. Get our scatter plot. This is what this thing looks like. It looks very, very much like this plot right here. Correlation coefficient. Okay, so let's go back to stat. We get a correlation coefficient by doing a linear regression. Let's just do a simple linear regression because that gets us everything. Our X is going to be distance from the star, Y is the year, and let's just scroll down, and for the heck of it, let's just add a fitted line plot and a residual versus X values plot, just so that we have them all at our fingertips in case we're asked about them later. So, okay, we are given the correlation coefficient here. It's pretty strong. 3 decimal places will be 0.989. Is that a linear relationship? Absolutely, yes. You can also get that from the from this table. you'll see under the slope parameter, you'll see actually the question of whether or not, yeah, it's answered really here. This p-value is the p-value associated with the correlation coefficient. It's a very, very, very low, so we would absolutely confirm that yes, there is a linear relationship. The same question is answered down here in this section called Analysis of Variance. Basically, this p-value that is at the very to the right of the table, if that p-value is extremely low, then we would conclude absolutely there is a linear relationship. And how low it needs to be, it really depends on what significance level you've chosen, but we'll probably use 0.05 most of the time. Okay, the regression line, it was a good thing that we did this because it's asking us for it. So the intercept is negative 12.2 and the slope is 0.06. So we want a positive slope and a negative intercept. So there you go. That looks right. And let's see, plot the residuals. Yep, I knew it. We needed a residual plot. So let's look at the residual plot. Here is the residual plot. Oh, there's a bit of a shape there. Look at that curve. This is the residual plot. It wasn't so apparent. I mean, this is it looks pretty linear, but you can actually see the points are above the line of best fit, and then they're below the line of best fit, and then they're above the line of best fit. Right? Look at that. So this is the residual plot, and it has a shape to it. Now, this normally is an indication, do you think the least squares regression line is a good model? The one reason to say it's not a good model is because of this shape on the residuals. The correlation coefficient is really, really high, but part of it is because the data is so spread out. If you so I would say because you have this shape, I think that there's a linear relationship is not actually going to be the best model. I'm going to say no. Really, in order for you to conclude that a linear model is really good, you need a strong correlation coefficient, and you need those residuals to look good. You want to have a good scattering, a good random pattern. You don't want to have any shape like this curvy shape. This curvy shape, I should say. That's indication that a linear model actually isn't the best model. There are other regression models that you can work with, which we're not covering in this module. We cover later. Okay. Well, thanks for sticking with me through this. I hope this helps you as you go through the homework this week, and I will be in touch later. All right, bye.